Let's begin with the event itself. In Alaska, a wave measuring 1,585 feet in height was generated inside a narrow fjord. To give you perspective, that is taller than the Empire State Building. It is taller than the Petronas Towers. It is, quite literally, one of the highest waves ever recorded on Earth. Now, the obvious question is, what caused this? How do you end up with a wall of water higher than a skyscraper in a place where no earthquake was recorded and no storm was underway? The answer is found in the relationship between mountains, glaciers, and the sea. The coast of southeastern Alaska is carved by fjords. These are long, narrow valleys with steep walls created over tens of thousands of years by glacial ice. As glaciers retreat, they leave behind sheer cliffs, fractured rock, and unstable slopes. To the casual eye, the scenery looks permanent, solid granite walls, ice, and water. But geologically, it is in motion. Think of these fjords as natural laboratories of instability. The rock faces are weakened by freeze-thaw cycles, where water seeps into cracks, freezes, and expands. Glacial ice, which once supported and braced entire slopes, is melting away. The result is that mountain walls are essentially being unpinned. They are left hanging over deep water, waiting for gravity to take over. On the day of the event, a massive section of mountainside collapsed. Not slowly, not in pieces, but at all once. We estimate that hundreds of millions of cubic meters of rock plunged into the fjord in a matter of seconds. Imagine tens of thousands of Olympic-sized swimming pools filled with solid rock all being dumped suddenly into a bathtub. That is the closest analogy we can use. This was not a classic earthquake-driven tsunami. It was a landslide-generated megatsunami. The distinction matters. Earthquakes displace the seafloor, pushing up a wave. In contrast, here, the wave was generated by the impact of rock and debris slamming into the water column. When that volume of material struck, it displaced the entire fjord's water column. The wave had no place to go but upward.
Now, why was the wave so tall? The narrow shape of a fjord acts like a funnel. When water is displaced in such a confined space, it rebounds violently. Geologists call this the bathtub effect. Push water to one end of a narrow container, and it surges back with equal force. The collapse displaced water against one wall of the fjord, which then surged back, climbing higher and higher. In seconds, the wave reached an unimaginable height, over 1,500 feet. Close to the source, the wave stripped entire mountainsides of trees. Every trace of vegetation was scoured away. Rocks were polished bare. In aerial photographs, you can literally see the clean line of destruction where the wave reached its peak. Few people witnessed the event directly, and that is fortunate. A cruise ship, had it been inside the fjord at the time, would have stood no chance. But there were observers. Local boat captains reported unusual tidal behavior, the water suddenly retreating, then surging back. Even over 70 miles away in Juneau, tidal gauges recorded abnormal fluctuations for hours. Campers and kayakers in the region were caught off guard. Some described hearing what sounded like a thunderclap, followed by a roar that grew into a deafening wall of sound. One group later found their kayaks lodged in trees, carried upward by the force of the water. Seismometers across Alaska and even into Canada registered the landslide as a distinct event, not as a traditional earthquake, but as a ground-shaking collapse. Alaska's state seismologist, Michael West, compared it to an entire mountainside failing in a single instant. And that is exactly what it was. From satellite imagery, scientists calculated both the volume of rock involved and the run-up height of the wave. That figure, 1,585 feet, is now listed among the tallest megatsunamis ever documented. But the most striking observation was this. The event was preceded by small tremors, microseismic activity. Essentially, faint warning signs rippled through the region before the final collapse. This suggests that landslide-generated tsunamis may in some cases provide detectable precursors. For scientists, that is a breakthrough worth investigating.
This was not the first time Alaska experienced such a catastrophe. In 1958, in Lituya Bay, a landslide produced a wave that ran up to 1,720 feet. That record still stands as the highest known wave in human history. The recent event fits into the same category. Mountain walls weakened by retreating glaciers, collapsing catastrophically into confined fjords. The pattern is unmistakable. And Alaska is not alone. Norway, Greenland, British Columbia all have fjords where glaciers are pulling back, where slopes are left unsupported. As climate change accelerates ice loss, the probability of similar landslide-driven tsunamis increases. Now, you might ask, if these areas are remote, why should we be concerned? The answer is twofold. First, these regions are not empty. Fishing boats, cruise ships, and local communities depend on fjord waters. A megatsunami occurring when vessels are present could be catastrophic. Second, these events are signals. They remind us that mountains are not permanent fixtures. They are dynamic systems. And when ice, nature's glue, disappears, collapse can follow. The lesson extends beyond Alaska. Any steep valley carved by glaciers, anywhere in the world, carries the same risks.